You know, I remember the exact moment I realized we weren't alone in this cosmic dance. Not because of little green men or flying saucers, but because something came knocking on our door from another star system. And now, it's happened again. Except this time, what's arrived is stranger, more active, and more baffling than anything we've seen before. On July 1st, 2025, astronomers in Chile pointed their telescopes at a particular patch of sky and discovered something that shouldn't exist according to everything we thought we knew about comets. They called it 3I/Atlas, and here's what keeps me awake at night. This object is releasing chemicals that natural comets shouldn't produce. It's changing colors like some kind of cosmic chameleon, shifting from red to green to blue. It's accelerating in ways that gravity alone cannot explain. And yes, while the clickbait headlines scream that it's as big as Manhattan, the truth is somehow more fascinating and more unsettling than the hype. Because the solid core might be smaller than Manhattan, but the cloud of gas and dust surrounding it, the coma, is so massive it could swallow our entire planet several times over. We're talking about a sphere of material 348,000 kilometers wide. That's almost the distance from Earth to the Moon. But size isn't what has scientists like me losing sleep. It's what this thing is doing. It's what it's made of. And it's the uncomfortable questions it forces us to ask about intelligence, about design, and about what might be traveling between the stars right now, hurtling toward us at 68 kilometers per second. Let me be clear with you right from the start. I'm not here to peddle conspiracy theories or sensationalism. I'm a theoretical physicist. I've spent my entire life studying the laws that govern reality itself, from the smallest quantum particles to the largest structures in the universe. And when something appears in our solar system that behaves in ways our laws struggle to explain, that's not a moment for panic. It's a moment for radical curiosity. It's a moment to ask deeper questions, because 3I/Atlas isn't just another space rock. It's a messenger from beyond our cosmic neighborhood, carrying information about star systems we've never visited, chemical processes we've never witnessed, and possibly, just possibly, something that challenges our fundamental understanding of what's natural and what's designed. So, let me take you on a journey, not just through the science of this extraordinary object, but through the implications of its existence, what it means for our place in the universe, what it reveals about the boundaries between natural and artificial, and why this moment, right now, as this interstellar visitor makes its closest approach to Earth, represents one of the most significant scientific opportunities in human history. By the time we're done, you're going to see the night sky differently. You're going to understand why some of the brightest minds in astrophysics are pointing every instrument we have at this one object. And you're going to confront a question that philosophers and scientists have wrestled with for centuries. Are we truly alone, or are we simply not paying close enough attention to what's passing through our backyard? The story begins in the Atacama Desert of Chile, one of the driest places on Earth and consequently one of the best locations on the planet for astronomy. The Atlas Survey, that's the Asteroid Terrestrial Impact Last Alert System, operates telescopes there specifically designed to detect objects that might pose a threat to Earth or that display unusual characteristics. On that summer day in July 2025, their automated systems flagged something peculiar, an object moving through space on a trajectory that didn't fit. You see, every planet, asteroid, and comet born in our solar system follows certain rules. They orbit the sun in elliptical paths. Their speeds fall within predictable ranges. Their trajectories can be traced backward to origins within our cosmic neighborhood. But this object was different. Its path was hyperbolic, not elliptical. That single word, hyperbolic, changes everything. Let me explain what that means. Imagine you're on a swing set. No matter how high you swing, you always come back down, back and forth, in an ellipse. That's how objects bound to our solar system behave. They're on that cosmic swing, trapped by the sun's gravity, destined to orbit forever unless something catastrophic happens. But now imagine someone gives you such an enormous push that you break free of the swing entirely. You go up and never come back. You escape. That's a hyperbolic trajectory. 3I/Atlas is on that swing that's been pushed so hard it broke free, but in reverse. It came from outside, swung around our sun, and now it's heading back out into the infinite darkness of interstellar space. Its orbital eccentricity is 6.1374. Anything above 1 means you're not coming back. This thing is clocking in at over 6. It's a cosmic hit and run. When astronomers calculated its velocity, they found it was moving at approximately 68 kilometers per second. To put that in perspective, the fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches about 192 kilometers per second at its peak, and that's only when it's diving close to the sun, using gravity to accelerate. 3I/Atlas is naturally moving at speeds that most solar system objects never achieve. It's a bullet fired from another star system, and we just happened to be in the neighborhood when it passed through. This makes 3I/Atlas only the third confirmed interstellar object we've ever detected. The first was Oumuamua, discovered in 2017, that strange cigar-shaped or perhaps pancake-shaped object that accelerated as it left the solar system in ways that still spark heated debates in scientific conferences. The second was 2I/Borisov in 2019, which looked and behaved much more like a typical comet, giving us some relief that maybe the universe wasn't trying to mess with our heads after all. And now we have 3I/Atlas, and let me tell you, this one is bringing back all the strangeness of Oumuamua while adding its own unique flavors of weird. Now let's address the Manhattan comparison, because this is where science journalism often fails us, trading accuracy for clicks. You've probably seen the headlines. Interstellar comet the size of Manhattan threatens Earth. Massive object could cover New York City. And look, I understand the appeal. Manhattan is something we can visualize. It's concrete, literally and figuratively. We know its size, its shape, its significance. Saying something is the size of Manhattan immediately communicates scale in a way that saying it's 5 kilometers in diameter doesn't quite capture for most people. But here's the problem. It's not accurate. And in science, accuracy matters because it's the foundation of understanding. Manhattan Island is approximately 59 square kilometers in area. It stretches about 21.6 kilometers from north to south and varies from about 1.4 to 3.7 kilometers from east to west. It's home to over 1.5 million people. Its skyline is iconic. Its mass, if we could somehow weigh the entire island, including all the buildings and infrastructure, would be absolutely enormous. So when someone says 3I/Atlas is the size of Manhattan, your brain probably conjures an image of this massive solid object, this island-sized chunk of ice and rock hurtling through space, and that mental image is fundamentally misleading. The actual nucleus of 3I/Atlas, the solid core of the comet, is estimated to be somewhere between 0.32 and 5.6 kilometers in diameter. Let's be generous and take the upper estimate. A sphere 5.6 kilometers in diameter would have a surface area of roughly 98.5 square kilometers, if we're talking about its surface. But that's not quite the right comparison either, because Manhattan is essentially two-dimensional, a flat area, while the comet nucleus is three-dimensional. If we tried to compare the cross-sectional area, the shadow it would cast if you shined a light on it, we'd be looking at about 24.6 square kilometers for a 5.6 kilometer diameter sphere. That's less than half the area of Manhattan. And if the nucleus is on the smaller end of the estimates, we're talking about something less than 1 square kilometer in cross-section. That's smaller than Central Park. So where did the Manhattan comparison come from? The answer lies not in the nucleus, but in the coma. And this is where 3I/Atlas becomes genuinely extraordinary. The coma is the vast cloud of gas and dust that surrounds the nucleus of a comet. When a comet approaches the sun, solar radiation heats its surface. Ice sublimates, turning directly from solid to gas without becoming liquid first. This gas expands outward, carrying dust particles with it, creating an enormous atmosphere around the tiny solid core. For most comets, this coma can be quite large, sometimes hundreds of thousands of kilometers across. But 3I/ATLAS has taken this to an extreme that has scientists genuinely surprised. The dust coma of 3I/Atlas measures approximately 26,400 kilometers by 24,700 kilometers. That's not a typo. We're talking about a cloud of material large enough to fit several Earths side by side, but that's just the dust. The carbon dioxide coma, the envelope of CO2 gas, extends even further, with a radius of approximately 348,000 kilometers. The average distance from Earth to the Moon is 384,000 kilometers. This comet is wearing a coat of gas that's nearly as wide as the Earth-Moon system. If you could somehow see this gas cloud with your naked eye, if it glowed bright enough, it would appear larger in the sky than the Moon when it's at its closest approach to Earth. This is what could cover Manhattan, not the solid nucleus, but this ghostly, ethereal, mostly transparent cloud of gas and dust. You could fly Manhattan right through most of that coma and not hit anything solid. You'd barely notice it except for perhaps some light scattering and a bit of a haze. It's the difference between being hit by a bowling ball and being hit by a fog bank the size of the bowling ball. Both are technically the same size, but one will hurt a lot more than the other. But here's what makes this more than just a semantic argument about measurements. The reason the coma is so massive isn't just because 3I/Atlas is close to the Sunday. It's because this comet is extraordinarily active. It's outgassing at rates that are unusual even for interstellar objects. And it's not just the quantity that's strange, it's the composition. 3I/Atlas is releasing approximately 129 kilograms of carbon dioxide every single second. That's the weight of about 2 adult humans' worth of CO2 gas every second, continuously, for months. It's also releasing about 6.6 kilograms of water vapor per second, along with carbon monoxide, hydrogen cyanide, and here's where it gets really interesting, nickel vapor. Let me pause on that for a moment. Nickel vapor. Nickel is a metal. It has a boiling point of 2,913 degrees Celsius. For a comet to be releasing nickel vapor, something on or in that comet has to be reaching extraordinarily high temperatures, or there has to be some chemical process we don't fully understand that's liberating nickel atoms and sending them out into space. This isn't typical. Oh sure, we've detected metals in comets before. Sodium, iron, even nickel in trace amounts. But the quantities and the manner in which 3I/Atlas is releasing these materials has raised eyebrows. Some scientists suggest it could be due to impacts of dust grains on the nucleus creating momentary high temperature events. Others wonder if there are chemical reactions occurring on the surface that we haven't accounted for. And a few, a very small but vocal few, ask whether this pattern of outgassing could be consistent with something other than natural sublimation. Then there are the color changes. This is perhaps the most visually striking anomaly. When 3I/Atlas was first observed in July, it appeared distinctly reddish in color. This makes sense. Many comets have reddish hues due to organic compounds and tholins, these complex molecules formed by radiation acting on simpler chemicals. Red is comfortable. Red is normal. But then, as weeks passed and the comet drew closer to the Sun, observers noticed it was turning green, specifically a vivid emerald green. This color in comets typically comes from diatomic carbon, 2 carbon atoms bonded together, or from cyanogen, a toxic gas made of carbon and nitrogen. Green comets aren't unheard of. We see them occasionally, but the transition from red to green was unusually pronounced. And then, in what has to be one of the most puzzling developments, some observations captured blue emissions as well. Blue in a comet usually comes from ionized carbon monoxide or other ions glowing under solar wind bombardment. To see a comet cycle through red, green, and blue is like watching a cosmic traffic light. Each color tells us about the chemistry and physics happening at that moment, but the sequence and intensity of the changes in 3I/Atlas don't perfectly match our models of typical cometary behavior. Beyond the colors and the composition, there's the issue of non-gravitational acceleration. This is the smoking gun that makes 3I/Atlas so intriguing to some researchers. When we track a comet's trajectory, we expect gravity to dominate its path. The Sun pulls it in, the planets exert their subtle tugs, and we can predict where it should be with remarkable precision. But sometimes comets don't follow the script. They accelerate or decelerate in ways that gravity alone cannot explain. This is non-gravitational acceleration, and it's usually caused by outgassing. As ice vaporizes on the sunlit side, it jets away from the nucleus like tiny rocket engines, pushing the comet slightly off course. For most comets, this effect is well understood and predictable. We see it, we measure it, we factor it into our calculations. But 3I/Atlas presented something unusual. The magnitude and pattern of its non-gravitational acceleration didn't quite fit the standard cometary model. It was as if the object was experiencing forces that were either stronger than expected or oriented in unexpected directions. Now, you might say, well, maybe it just had an unusually active surface or an irregular shape that channeled the gas jets in odd ways, and that's possible. Comets are messy, chaotic objects, and they don't always behave according to our neat equations. But here's where it gets fascinating. When you combine the unusual acceleration with the atypical spectroscopic signatures and the strange trajectory, you start to see why some scientists began to wonder if we were looking at the full picture. Could there be internal structures we're not accounting for? Could the composition be more exotic than we initially thought? Or, and this is the question that makes headlines but requires extraordinary evidence, could there be something artificial influencing its behavior? Now, I want to be crystal clear here. The scientific community is not claiming that 3I/Atlas is an alien spacecraft. What we're saying is that it exhibits a combination of characteristics that don't perfectly align with our current models of what a typical comet should be. And in science, when something doesn't fit, we investigate. We don't jump to conclusions, but we also don't ignore anomalies. Now, let me walk you through some of the specific anomalies that made scientists pause and take a second look at Oumuamua. First, there's the acceleration problem. As Oumuamua was leaving our solar system, astronomers noticed something peculiar. It was speeding up, not dramatically but measurably. It was accelerating away from the sun in a way that gravity alone couldn't explain. Now, for a comet, this isn't necessarily shocking. Comets accelerate all the time due to something called the rocket effect. When a comet gets close to the sun, the ice on its surface vaporizes, creating jets of gas that push the comet like tiny rocket engines. We've seen this countless times. It's perfectly normal. But here's the catch. Oumuamua showed no visible signs of outgassing, no tail, no coma, no detectable emissions, and yet it was accelerating. Avi Loeb, the chair of Harvard's astronomy department, put it beautifully when he said that this was like watching a car accelerate down a highway with no visible engine running. You can see the motion, you can measure the speed, but you can't see what's causing it. Some scientists propose that perhaps Oumuamua was releasing gas, but in a way we couldn't detect. Maybe it was venting from one specific spot, or perhaps the composition was such that it didn't create a visible coma. These are reasonable explanations, and they might very well be correct. But they require us to make assumptions about Oumuamua that we don't make about other comets. We're essentially creating special conditions to make it fit our models. And while that's not necessarily wrong, it does highlight that this object is, at minimum, unusual. Then there's the shape issue, which I mentioned earlier. The extreme elongation suggested by the light curve is rare, but not impossible, in nature. However, it does raise questions. How does such a fragile, elongated structure survive the stresses of interstellar travel? Why haven't we seen more objects like this? Add to this the fact that Oumuamua appeared to be tumbling through space in a complex rotation, and you have an object that defies easy categorization. Now, some astronomers have proposed that Oumuamua might be a natural phenomenon we've simply never encountered before. Perhaps a fragment of a planet torn apart by tidal forces as it passed too close to its star. Or maybe it's what's called a hydrogen iceberg, a chunk of frozen hydrogen that formed in the coldest reaches of a giant molecular cloud. This theory would explain the acceleration without visible outgassing the hydrogen sublimates so cleanly it's invisible. These are fascinating hypotheses. They push the boundaries of our understanding of planetary formation and the exotic objects that might exist in the dark spaces between stars. But here's what troubles me. We're essentially inventing new categories of astronomical objects to explain a single data point. That's not necessarily wrong. Science often progresses this way, but it does make you wonder if we're missing something more fundamental. The SETI implications cannot be ignored. Several serious scientists, including my colleague Avi Loeb at Harvard, have suggested we must at least consider the possibility that Oumuamua could be artificial, perhaps a light sail, a thin reflective sheet pushed by starlight, or even deliberately by an alien civilization. Before you dismiss this as science fiction, remember that we ourselves are developing this exact technology. The Breakthrough Starshot initiative aims to send tiny spacecraft to Alpha Centauri using precisely this method, gossamer-thin sails pushed by powerful lasers. If we're contemplating sending such probes to other star systems, why wouldn't an advanced civilization do the same? The mathematics of light sails predicts exactly the kind of acceleration Oumuamua exhibited. The extreme elongation could represent a collapsed or damaged sail tumbling through space, a derelict from some ancient voyage long abandoned. I want to be clear, I'm not saying Oumuamua is definitely alien technology. Extraordinary claims require extraordinary evidence, and we simply don't have enough data. What I am saying is that we cannot afford to let our assumptions blind us to possibilities that deserve investigation. The scientific method isn't about closing doors, it's about opening them, then rigorously testing what we find on the other side. And this brings me to a crucial point about how we search for intelligence beyond Earth. For decades, we've been listening. SETI, the search for extraterrestrial intelligence, has been scanning the cosmos for radio signals, looking for that telltale pattern that screams artificial. It's like sitting in a dark forest, hoping someone turns on a radio. But here's what troubles me. We're assuming they communicate the way we do. We're assuming they use electromagnetic radiation in frequencies we've decided to monitor. We're assuming they even want to be found. Think about it from their perspective for a moment. If you were a civilization millions of years more advanced than humanity, would you be broadcasting your presence to every primitive species capable of building a radio telescope? Or would you have moved beyond such crude communication methods entirely? Perhaps they communicate through quantum entanglement, sending information instantaneously across vast distances. Perhaps they've learned to manipulate the fabric of space-time itself, creating gravitational ripples we wouldn't recognize as messages. Perhaps they've transcended physical form altogether, existing as patterns of pure information in ways we can't even conceptualize. We're fish in the ocean looking for other fish, while someone might be walking on the shore just above the surface. This is why Oumuamua matters so much, not because of what it is, but because of what it represents. It's a reminder that the universe doesn't care about our expectations. Reality operates by its own rules, and those rules are often stranger than anything we imagine. And this is where we stand today, at a crossroads between two very different ways of understanding our place in the cosmos. On one hand, we have the universe as we've traditionally understood it, vast, ancient, mostly empty, with life emerging only under the rarest of circumstances. A cosmic lottery where Earth won the grand prize, and intelligence is so statistically improbable that we might be alone for thousands of light years in every direction. On the other hand, we have mounting evidence that challenges every assumption in that picture. Consider the speed at which life appeared on Earth. Our planet formed about 4.5 billion years ago. For the first few 100 million years, it was a hellscape molten rock, volcanic eruptions, asteroid bombardments. The surface didn't even fully solidify until about 4.4 billion years ago. And yet, we have evidence of life, or at least complex organic chemistry, dating back 4.1 billion years. That's barely 300 million years after the planet became habitable. In cosmic terms, that's instantaneous. Think about what that means. Life didn't wait around. It didn't take billions of years of random chemical accidents to eventually stumble into existence. It appeared almost immediately, as soon as conditions permitted. That's like throwing the ingredients for a cake into a bowl and finding it already baked before you can turn on the oven. This suggests one of two possibilities. Either the chemistry that leads to life is far more inevitable than we thought, almost like a chemical imperative written into the laws of physics, or life didn't actually originate on Earth at all. Perhaps it arrived here, already formed from somewhere else. And then there's the question of intelligence. We used to think intelligence was an evolutionary fluke, a one-time accident that happened only because of a specific sequence of unlikely events on Earth. But the more we study evolution, the more we realize that intelligence keeps emerging independently. Octopuses evolved intelligence completely separately from vertebrates. Their last common ancestor with us was a simple worm-like creature 600 million years ago. Yet they solve puzzles, use tools, recognize individual humans, and appear to have complex inner lives. Ravens and parrots demonstrate problem-solving abilities that rival great apes. Dolphins have cultures, they pass knowledge from generation to generation. Elephants mourn their dead and seem to have a concept of self. Intelligence isn't rare, it's convergent. Evolution keeps discovering it, over and over, through completely different pathways. So if intelligence emerges repeatedly on a single planet, what happens across billions of planets over billions of years? This is the paradox we're living in. Every logical inference tells us the universe should be teeming with intelligence, yet we see no evidence of it, unless we're looking in the wrong places, or for the wrong things. Perhaps the great silence tells us something even more profound about consciousness itself. You see, we've been assuming that intelligence follows a certain trajectory, that consciousness, once it emerges, inevitably seeks to expand, to explore, to communicate across the cosmos. But what if we're wrong about that fundamental assumption? What if advanced consciousness doesn't expand outward at all, but inward? Think about it. Every meditation, tradition, every contemplative practice throughout human history has discovered the same thing, that the universe within can be just as infinite as the universe without. What if Type 3 civilizations aren't building Dyson spheres? What if they're building inner worlds so rich, so complex, so satisfying that physical reality becomes optional? Imagine a civilization that's mastered not just physics, but consciousness itself. They could simulate entire universes in their minds, create experiences more vivid than any physical journey, explore mathematical dimensions we can't even conceive of. Why would they bother transmitting radio signals? Why colonize planets when you can create perfect worlds in consciousness? Why reach across light years when infinity exists between your thoughts? This is what the philosopher Robert Nozick called the experience machine problem, taken to its cosmic extreme. And here's the unsettling part. If this is the fate of all advanced civilizations, it might be our fate too. We're already seeing the early signs: virtual reality, neural interfaces, the promise of uploading consciousness. We're building the technology to turn inward, to leave physical reality behind. Every year, our digital worlds become more immersive, more compelling than the physical one. What happens in 1,000 years? 1,000,000? Do we become like those advanced civilizations, silent, invisible, lost in inner infinities, while the physical universe goes dark around us? Or perhaps, and this is even stranger, perhaps consciousness itself transcends what we think of as individual existence entirely. Maybe the endpoint of intelligence isn't preservation of self at all, but dissolution into something larger, a cosmic consciousness that doesn't need bodies or signals or any of the things we're looking for. The mystics have been saying this for millennia, that separation is illusion, that ultimately all consciousness is one. What if they're right? What if advanced civilizations discover this empirically? Then the great silence wouldn't be silence at all. It would be the sound of everyone returning home to a unity we never left. And perhaps, just perhaps, that unity is already calling to us. Think about the strangest phenomena in our universe: dark energy, which makes up 68% of everything that exists, yet remains completely invisible to us. It's pushing the universe apart, accelerating expansion in a way that defies our understanding of gravity. We've measured it, we've confirmed it, but we have no idea what it is. What if it's not a thing at all? What if it's the tension of consciousness trying to reconcile multiplicity with unity, the universe literally stretching itself between the illusion of separation and the reality of oneness? I'm not saying abandon physics for mysticism. I'm saying maybe they're describing the same truth from different angles. The equations point to something our intuition has always known. And here's where it gets personal. where this cosmic philosophy becomes immediate and urgent. If consciousness is fundamental, if the universe is the self-observation of a unified field, then every act of cruelty, every moment of indifference, every time we dehumanize another person, we're doing it to ourselves, not metaphorically, literally. When I look into your eyes, I'm not seeing another. I'm seeing another aperture through which the universe peers at itself. The same awareness that's reading these words right now is the same awareness experiencing life as every person you've ever met, every person you've ever hurt, every person you've ever loved. This isn't just philosophy. It changes everything. It means that compassion isn't a virtue we cultivate. It's the recognition of truth. When you help someone, you're not being altruistic, you're being rational. You're acknowledging the fundamental structure of reality. It means that the quest for immortality, which drives so much of our technology and our fear, might be based on a misunderstanding. You're already immortal. The consciousness experiencing your life right now has been experiencing existence since existence began and will continue after this particular configuration of atoms disperses. You've already lived every life that has ever been lived. You just don't remember, because memory is a function of the brain, not consciousness itself. This perspective, this understanding, if I'm right, if the scientists and mystics who've glimpsed this truth are right, it's the final frontier. Not Mars, not the Andromeda galaxy, but the recognition of what we've always been. And maybe the reason we haven't met aliens isn't because they're not out there. Maybe it's because any civilization that achieves the technology to traverse the cosmos also achieves the wisdom to recognize that there's nowhere to go. The greatest journey isn't outward, it's inward.